Right, so continuing with time study methods for ODEs. To recap where we've been. So we're looking at this general first order initial value problem. Y prime equals MTY, and I guess I should state the entire initial value problem. Initial condition. So what we saw last time is the simplest time study method, Euler's method. And we also saw that the error in Euler's method is proportional to h, which is the time step size. So yes, the method converges, and that's the difference between the computed solution and the exact solution does go to zero, as h goes to zero. But since the error is only proportional to h to the first power as opposed to a higher power, convergence to the exact solution is slow. What we like to do is see if we can get a higher order accurate method. So the error would be order h to the p, where p is some power greater than 1. Remember, you don't want to have the textbook up at some point. Okay. Now, the most straightforward way to get higher order accuracy is to generalize what was done in Euler's method. Euler's method, what we did was we computed, we took a Taylor expansion of y of t around like time tn, which is like the last time at which we have a solution, to get the solution at a new time. And then we just took only the first two terms of that Taylor expansion involving y and y prime, and then that's Euler's method. So if that gave us first order accuracy, it makes sense that if you were to retain additional terms of the Taylor expansion, then yes, we would get higher order accuracy. But there's one compelling reason not to do that is, like, suppose we want to include the third term of a Taylor expansion, which is y double prime. Well, y prime is what I'm saying here. So as an example, can get second order accuracy if we compute something like this: yn plus 1 is equal to ym plus, the first one I'm writing out is just Euler's method. And then I add an additional term, 1/2 h squared times, so then we have, we want to approximate y double prime. So at time tn, but that would be equal to the derivative of f of t y of t and then evaluating that derivative but then to evaluate this derivative of f, we need a partial derivative of f with respect to t, and also a partial derivative of f with respect to y times dy dt. So we have to approximate derivatives of f. So it's kind of like Newton's method. Newton's method is a trade-off. You get more rapid convergence for Newton's method than other root-finding methods, but you need to evaluate f prime, and that might not be practical. So same situation here. You can use as many terms in your Taylor expansions as you would like, but then you have to deal with higher order derivatives. So we like this, and what we'd like to do is see if we get higher order accuracy without having to do this at all. And this is how we arrive at Runge-Kutta methods. So the idea behind Runge-Kutta methods is that instead of evaluating f just once, like an Euler's method, if we evaluate f multiple times, the time values that are between time tn and time tn plus 1. So here's where we're at, and here's where we're trying to get to. Try to get higher order accuracy that way instead of needing derivatives of f. So to give you an idea, I'll give you an example of how a Runge-Kutta method can be derived. So we're going to impose a method as a structure on the method. So it's going to be something in this form. So we have two evaluations of f. One of them is at with the same arguments as for Euler's method, but then we have a second evaluation of f here at a different time and a different solution value. And we have four unknowns. So we have a and b, that's scale the evaluations of f. And then we have alpha and beta to evaluate f at a different point in the ty plane. So the goal here is we want to get second order accuracy with a method like this. So first what I do is I take a Taylor expansion of the exact solution with center t to evaluate y of t plus h. So think of this, if you think of this as tn and then this is tn plus 1. So now I take my Taylor expansion out to the order h squared term. I'm going to have additional terms that are order h cubed that I won't need to get into. Now, so I want to match this Taylor expansion of f with my method, and I want this agreement to occur up through terms of order h squared. For second order accuracy. Now, as you can see, portions of these lines already match. We already have same left sides. We have y of t plus h times something on the right side in both equations. So I'm going to strip out the parts that already do match, so that we can focus on what needs to match. So for instance, from this first line, I'm taking only these terms, and notice there's a common factor of h, so I've stripped that out too. And then in the second equation, I've just taken this part, and again, the common factor of h that has been removed. So now I just need to match this part through this part, at least through terms of order h. So then when I put these matching expressions back in here, these equations will match through order h squared. So questions about this whole matching thing? So what I do is, for this first expression here, I go ahead and carry out the differentiation of this whole expression, f of t, y of t. So both arguments depend on t. And that's why when I take a derivative of this whole thing with respect to t, I end up with partial derivative of f with respect to t over here, and then partial f with respect to y here. But then I have to take a derivative of this argument with respect to t, and that gives, but y prime of t is f of ty, so that causes this factor of f to appear here. So the whole derivative is df dt plus df dy, dy dt. Okay, I'm going to put this part on a new page so we can easily see what we're matching against. Okay. Now, for this part right here, particularly this evaluation of f, I'm going to carry out a what's called a multivariable Taylor expansion. So multivariable Taylor expansion, it's not really any different. It's natural generalization of the ordinary Taylor expansion. But because you're dealing with a function of several variables, you have to take partial derivatives with respect to each one. So what I end up with is, okay, so I have this part stays the same, and then I have b times my multivariable Taylor expansion. The first term is just going to be f of t y of t, which is the center of my multivariable Taylor expansion. And then for a second term of that multivariable Taylor expansion, I go ahead and take partial respect of f respect to t times the change in t, which is alpha, plus partial of f with respect to y times the change in y, which is beta. So now we have this Taylor expanded, but only through the first derivative term. We don't need to go any further than that. So now I need to match this against this, which I can do because I have f dft dfty here, I have f dft dfty here, and I just have to set a, b, alpha, and beta so that these expressions match up through terms of order h. So, for instance, here I have f of t, y of t, here and here, but the second one is a coefficient of a plus b, so a plus b needs to be equal to 1. Here I have df dt times h over 2. Here I have df dt times alpha b, so alpha b has to be h over 2. And finally, I have df dy times h over 2f. And here I have df dy times b times beta. So b times beta must equal h over 2f. So by choosing a, b, alpha, and beta to satisfy these three equations, then these will match, and I will have a second order accurate method. So any question about this matching process? Now, this system, I have 4 unknowns, 3 equations. So this system of equations does not have a unique solution. I have multiple options, so I want to point out 2 of them. So for example, if I set a equals 0, b equal 1 for this equation, and then that would pin down alpha as h over 2, and then beta is h over 2 times f. Then I get this method. This is called the midpoint method. So, what I'm doing is instead of doing as an Euler's method where I use a time derivative at Tn, Yn, I want to approximate y prime at the midpoint in time. So Tn plus half a time step. But for that, I need the approximation of a solution at time Tn plus half a time step. To get this approximation, I use Euler's method with half a time step. So now I have f of Tn plus a half, Yn plus a half, where the latter is approximated. Another way of thinking about it is, since this derivative is evaluating the midpoint in time, Tn plus h over 2, I can think of Yn plus 1 minus Yn over h as, in Euler's method, we use that as an approximation of the derivative at time Tn. That's a forward difference. But I can also think of Yn plus 1 minus Yn over h as a second order accurate approximation of the time derivative at Tn plus h over 2. In other words, a center difference. So that's why we end up with second order accuracy. And we're using a more accurate time derivative formula. Option number 2. I said a and b both equal to 1/2. And that would require that alpha equals h, and then beta is equal to h times f. So now I have this method. This is called the explicit trapezoidal method. If you remember from last semester when we looked at methods for numerical integration, two methods we learned about were the midpoint rule, where you just evaluate your integrand at the midpoint of your interval AB, and we also learned about the trapezoidal rule. So you can think of these as being based on these simple quadrature rules. So here we're evaluating our at time tn. Here we're evaluating time tn plus 1. But at time tn plus 1, we need some approximation of a solution at that time. So again, we use Euler's method, but this time taking a full time step rather than a half time step. So another way of looking at it is, if I take my ODE and I integrate both sides with respect to t from time tn to tn plus 1, then I have this integral form of a solution. So the midpoint method comes about from using a midpoint rule on this integral. And the trapezoidal method comes from using the trapezoidal rule to approximate this integral. And we know that the methods are second order accurate because the first, when we look at the methods that are originally written out, the first terms that did not match were order h cubed. And that leads to the actual error being order h squared. Okay, so here are two of the simplest Runge-Kutta methods. So, questions on how these methods came about? A common way of writing Runge-Kutta methods is stages. Stages refer to evaluations of f. So for like the midpoint method, you first compute k1, which is h times f at time tn and then yn. And then we evaluate k2, which is approximating derivative y prime at the time tn plus half a time step. And to approximate y at that time, we use the k1 that we computed earlier down here. I should write this a little more clearly. And then I dot to my solution, y plus 1 is yn plus k2. For trapezoidal method, which is also known as the modified Euler's method, and we have the same k1 as before, but k2 is different. We're evaluating the time derivative at time tn plus h, so that we need a, since here we use yn plus k1 instead of 1/2 k1, to approximate a solution at time tn plus h instead of tn plus h over 2. And then we use both k's to update the solution from time tn to time tn plus 1. Now you can use more stages to get even higher order accuracy. By far the most well-known Runge-Kutta method is a fourth order. I'll show you that here. So here we have, so this is fourth order Runge-Kutta that uses 4 stages. So here we have the same stage, K1, as in the other two methods that I showed you. This is the same as the second stage from midpoint method. But then here we approximate the time derivative at the tn plus h over 2 again, but with a different y value that's using k2 instead of k1. And then here we use an approximation of a time derivative at time tn plus 1. So these 4 stages combined this way, which is reminiscent of Simpson's rule, because notice here we have the approximation of the time derivative at time tn, the left endpoint. Here tn plus 1, the right endpoint. And then these two both are for the midpoint in time, tn plus h over 2. Notice that the midpoint is 4 times as much weight as either endpoint, which is like Simpson's rule from numerical integration. So RK4, or 4-foot Runge-Kutta, a lot of times, very often when people need a higher accurate time step, maybe just go ahead and use this. And there are issues with it, as we'll see later when we talk about stiff systems, but it's something that's fairly easy to code up. Now, I should mention that all the examples I've shown you so far, even if we include Eulers, you think Eulers is like overly simple Runge-Kutta method. So far, the number of stages has been equal to the order of accuracy. That's not always true, though. So that's the spiel on Runge-Kutta methods, the basics anyway. So the idea is using multiple evaluations of f, or stages, to obtain higher order accuracy so that you don't have to evaluate higher order derivatives of f. Now, all the methods that I've shown you are also categorized as explicit methods. You can just basically plug and shut. You don't have to solve any equation or anything. Just take the information you're given, substitute it into your stages, grind it out, and then you have your solution at the due time. As opposed to an implicit method. So here's the simplest implicit method. It's called a backward Euler. Notice it looks a whole lot like forward Euler. The only difference between the two is in regular Euler's method, which is also known as forward Euler, to distinguish from backward Euler, f is evaluated at time tn and yn. That's information you have available. Here we're evaluating time derivative at time tn plus 1 and then yn plus 1. Yn plus 1 is what we're trying to compute. So our unknown appears on both sides of the equation. So it amounts to using a backward difference to approximate y prime at time tn plus 1, as opposed to using a forward difference to approximate y prime at time tn, which is what Euler's method does. So with y plus 1, our unknown, appearing on both sides of the equation, we have to solve for it. Now, if f is a linear function of y, then that's trivial to do. But otherwise, we have to use some iterative method, like Newton's method or maybe fixed point iteration, to take a time step. Now, that seems like a lot of work. Like, why would we go to so much trouble? In fact, implicit methods are more expensive on a per time step basis. So one time step of backward Euler for a nonlinear ODE is going to take more computational effort than regular Euler's method. So why do it? The reason is, and we'll see this later when we talk about stability, with implicit methods, you can often take fewer steps. So the overall computational effort may be less with an implicit method. And for certain problems, some people wouldn't dream of using an explicit method. They feel that implicit is the only way to go. I might not necessarily agree, but it's the conventional wisdom. And there's a fairly good reason for it. Now, for Euler's method, which I will refer to from this point on as forward Euler, is first order accurate. Backward Euler, also first order accurate. So if you carry out a conversion analysis like I did last time, that's a conclusion that you would arrive at. But there are higher order accurate implicit methods. For example, the trapezoidal method which to distinguish from the trapezoidal method I showed you earlier. Let me scroll back to that real quick. Okay, so here the explicit trapezoidal method, we only have y plus 1 here on the left side of the equation. Here we need the time derivative at tn plus 1, yn plus 1, and we use Euler's method to approximate that y value. And that's what leads to calling the explicit trapezoidal method, as opposed to just the trapezoidal method right here, where we don't try to approximate yn plus 1 here by Euler's method. We just put yn plus 1 here, so now it's on both sides of the equation. Now we have an implicit method. So we need to use some iteration to find yn plus 1 so that this equation is satisfied. And just like the explicit trapezoidal method, it's second order accurate. Now, one of the nice things about using an iteration, if you need to, for solving an ODE as opposed to other root finding problems, at least you have a built-in initial guess. Because if h is small, then a decent approximation of yn plus 1 is yn that you already have. Or you can expend a little computational effort to approximate the solution at time tn plus 1 this way using Euler's method. That's a decent initial guess. Because as we saw when we covered root finding methods, especially Newton's method, if you don't have a nearby initial guess, the method might diverge. But that's not really much of a concern here because you have a natural logical choice for initial guess. It's also not uncommon to not take many iterations, like if using Newton's method. If you have a low order time stepping method, it may only take just one Newton step. Because what's the point of iterating to a highly accurate root if there's going to be error in your method anyway from other sources? So a lot of time stepping methods that use Newton's method might probably only take one iteration. For a system of linear ODEs, so something in this form, like y prime equals ay. So y is a vector with n components, and a is the n by n matrix. So the backward Euler would look like this in this case. So then you go ahead and rearrange all terms of yn plus 1 on the left side, and we get this. We have an ax equals b problem, like from the first part of the semester. So we're solving a system of linear equations. This is our matrix. Yn, our previous solution, is on the right-hand side, and then our unknown is our solution at next time. Now, if this is your system of ODEs, where A is a constant matrix, independent of time, you end up having to solve this system many times where you have the same matrix, but the right-hand side is changing. So this what I was talking about when I first covered the LU decomposition. That if you have that situation where you're solving several system equations, same matrix in the right-hand sides, you compute the LU decomposition or whatever decomposition just once, and then you save that decomposition and reuse it from time step to time step. And this is exactly that situation. So you compute your LU factorization of this, or if you happen to know that this is symmetric positive definite, which can happen, like if this system ODEs is based on the PD equation, but you can do like a Cholesky factorization, whatever factorization you need, and then you keep reusing those factors. So in each time step, you're solving only two triangular systems. So it's not too much work per time step, especially if the matrix is banded, which actually does often happen in systems like this. So in that case, an implicit method may not be all that much more work than an explicit method. Oh, is that everything? Dang, that's everything. Wow, I wasn't even having a thought grade. Well, this is already asking questions. How's homework coming? Okay.
A very, very good question.
Homework 5. Homework 5.
Yeah, what about
Yeah, there's a question there.
okay. Which one?
The fixed points.
Okay, which one was it?
No, this one. Yeah. 10.35.
Oh, okay, yeah. Of this one?
Mm-hmm.
Okay, what about
I mean, my code runs and I don't get any output.
oh, okay. Does the function finish?
No.
Oh, it runs forever and ever.
Yes.
Oh, okay. So, what test case are you using? What equation are you using to solve?
I was using, you asked us to solve it with the first question, that is it?
One of the examples here, or?
Yeah, there's an example there. This one?
This one?
Mm-hmm.
Okay. That's strange. Okay. It's probably something, it might be a situation where you need to look at your code, because, probably spot pretty quickly what it is.
I don't have my laptop here.
Okay, you can send it to me later. Yeah, it's really got examples we can first. Other questions about anything? Yeah, I know I have a small amount of grading to catch up on, based on what's supposed to come in, but, I'm concerned about how much else needs to be submitted. So, when we have, well, maybe about 6 weeks to go, 5 or 6 weeks, something like that, so, still fine, but,
You're dropping the lowest too.
the lowest 2 get dropped, yeah, but that still leaves 7 homeworks in total.
Yeah.
Yeah, and some have not turned in many, so. Okay. You might have a choice to make as far as, the final is concerned, like what mode you want to be in. So, oral but comprehensive, or coding but non-comprehensive, pick your poison. Something for everybody to love and hate.
So the oral will be like, to say that we could just like focus on
The quizzes are a good thing to focus on.
on the quizzes.
Yeah.
Do we have any like mini exercises, like something on the board, like solve a problem?
That's a possibility, yeah. Yeah, so there are good things to look at. That option for final is like looking through the notes, like things how to derive things. I would not ask you to derive something on the spot, but maybe something where I guide you through it for the purpose of asking a certain question. Or yeah. But again, I mean, I don't want it to be something that drags out for a long time. So there's only so much suffering that can happen, for students. Well, I guess that'll do it.